So in this lecture, we have seen that we will see the dual form of the SVM formulations and how it is important from a primal problem of the SVM. So first write the primal form of SVM. What is the primal form? So till now what we have learned, this formulation is called the simple primal form of our SVM. So what we have learned till now, we have learned simply soft margin SVM and soft margin and hard margin SVM. But in general cases, we are using the soft margin SVM. Because why? Because in soft margin SVM, we are considering the misclassified point, but in natural, if you see the real database, they have always a misclassified point. So always we are considered the soft margin classified. Okay, so let's first write down the what is the soft margin classified, soft margin SVM equation. So first write down the soft margin first write down the soft margin SVM equations. Write down. So we in soft margin we have to find the minimum of overall W and B. We have to find the minimum. So half of norm of W plus C, that we call hyperparameter, in summations over all our zeta. N is our number of data points in our training data sets. Yes, this zeta is simply called the distance from the correct hyperplane to the misclassified point. Okay, we have already seen this thing, and we have some constant such that this constant is yi into W transpose xi plus b greater than is equals to 1 minus zeta I for all I. So we have got, if we have n number of points, we have got the such kind of n constant for each data point, and also there have one constant zeta is, that is always greater than is equals to 0. We have formulated this formula from soft margin SVM. Okay, so this formula is called the primal problem of the SVM. Okay, this is simply called the primal problem of SVM. Okay, simple. Yes, we are already. Now we are convert this thing. In the dual problem. Dual problem means what? Dual problem is nothing. It is the same equations in a different form, but both the equations in the equivalent. Okay, this is the one kind of, if you see, this is one kind of mathematical engineering techniques. Okay, if you are interested how to convert primal to dual, then if you are interested to learn details, then one chapter, there have one chapter, dual problem in optimization. In the world of in mathematics, there are one chapter, dual problem. Just revisit that chapter, you can easily find. So I am not, this is the not scope of this lecture, how to convert this problem to its dual problem. I am just seeing how this thing is equivalent, and how the important of visualizations of the dual problem is important to our next part of this video. Okay, so let's write down the dual problem of our this problem. So let's just write down the dual problem of our is. So the dual problem will be like this. So the dual problem will be, we want to maximize, just first write down, don't be confused, first write down, then I am discuss everything. But summation I is equals to 1 to n sum over alpha I minus 1 by 2 summation 1 I is equals to 1 to n minus summations j is equals to 1 to n alpha I alpha j yi yj and also there have x I x j, x I transpose x j. This is the dual problem of the equation, and this constant now is converted to where alpha I is greater than is equals to 0, and the sum I is equals to 1 to n alpha I yi is equals to 0. Okay, this is the dual form of this primal problem. These equations are the dual form of this. So both the equations are equivalent. Both the equations are the equivalent. They have no differences. Just I am transform these equations in this form. Okay. Now simple, if you just see, if you just geometrically visualize to the thing, if we have a query point at the end of the day, what have to find, what if we have at the end of the day we have to find the output of the classifier of the one query point. If we have give a query point, then we have to find its class level. This is our job actually in classifier. In the classifier technique, we have to find the class level of a query point. This is our main job. So if we have given a query point that we call xq, that is for query, we have denoted in suffix that xq. We have to find the w transpose xq plus b. We have find this thing, and if we call this thing f of xq, the simple functions of xq. Okay, and if we see if this value is positive, then our class level is properly correctly classified, and if this value is negative, then our class level is incorrectly classified. We have seen this thing in primary level. Okay, just it's depend on the sign of this function. So okay, its value now will calling the y. We have to find this at the end of the job. We have to calculate this thing. Now just compare these two things side by side. Okay, so here if you just see this thing, here we have here, just see this thing here if you just see here, we have taken the zeta term. Actually zeta is responsible for what? Zeta is responsible for all data point xi. We have seen in previous lecture, zeta is coming from all xi's for all misclassified point. If our class is correctly classified, then we got our zeta is 0. If our data point is misclassified, then only that we got our zeta I is greater than 0. If our data point is misclassified, then only zeta is greater than 0. If it is correctly classified, then zeta is equals to 0. We got it. So simple, zeta is responsible for our data points. Simple, just if you compare this thing zeta to alpha, so for alpha is represented same as zeta, means alpha is represented here same as our xi. So this is our first visualization. So just write these visualizations step by step. So our first visualizations is our xi will work in the primal problem. It will work same as alpha is that same as in dual problem. So both the things are same. This xi is work for our primal problem. This alpha is work for our dual problem. Okay, both these things are doing the same job. now the visualize the second thing. So the main observation is that here we have observed that here only here xi is occur here, w transpose xi, but if you see here only xi just occur this form, in this form, that is x transpose xj. Just this is the main, just visualize this thing. So here just write down this thing. So in our dual problem, xj's only occur in the form of xi transpose xj, only in the form of xi is occur here. If you just see here, xi is just form, just in dual problem xi occur in the form of this is the main important to extend this our SVM technique. This is the main important visualization. Now the third thing, if you visualize this thing, the third just thing, see the visualizations. So here x cube, just see this, just see our x cube problem, just write down first. In Primal problem, what we see our x cube, actually this one sign of this problem is actually our f of x cube, but our dual problem x cube, f of x cube, that is our functions of our query points will be like I is equals to 1 to n alpha I yi xi transpose xq plus p. Okay, this thing. Okay, this is the sample, just I am going to discuss it. If you are interested how it occurs, how it comes, just go to the Wikipedia or any SVM, any SVM books, then you can easily find how these query functions occur from our dual problem. And this is simply, this is the not scope of our problem, just I am comparing these three equations side by side, how these things are equivalent. I am not just finding the equations from primal to dual problem. Okay, I'm just compare this thing. Okay, just see this here, our query equations is at the for our query point we have using these equations, but for our dual problem we are using, for query point, for dual problem we are using these equations to find the class level of our query point. Okay, now the fourth visualization is if you see the fourth visualizations here, alpha I greater than 0. Okay, here alpha I is what, here actually here for support vectors, just see, just here for support vectors what we get, for support vectors we get that zeta I is get equals to 0. Okay, just see this thing, for support vectors we got the zeta I is equals to 0, and for misclassified point the zeta I is greater than 0. But here the main advantage of this problem here is we are simple here, alpha I is consider greater than is equals to 0 only for our support vectors. We are consider alpha is greater than 0 only for our support vectors. Okay, and alpha I is equals to 0 for non-support vectors. Okay, this is the main advantage to the dual problem of the SVM. So for non-support vectors we are not taking care about of it. Okay, just if you see, if alpha is greater than 0, then query equations, this portion will be totally 0. So it is not a matter our non-support vectors is it is not matter how much, just we have matter here our support vectors. Okay, so we see that our maximum number of point is non-support vectors and our minimum just some few points are care about support vectors. So for this region, this dual problem is very important, because of in this problem we are not care about non-support vectors, only we are care about our support vectors. For this reason, also for this reason, this technique it's called the support vector machine, because we are not taking care of non-support vectors, only we are taking care of our support vectors only, because of this, only for this reason. So first, so just rewrite this query equation. So first just rewrite these query equations again, then I am discussing. So what will be our xq? I'm just rewrite this equation again. Okay, this is our query equations, and for where we are get, here we are from fourth we are getting that from fourth observations, for support vectors we get that alpha I is greater than 0, and for non-support vectors we get that for alpha I is equals to 0. Okay, we are just see it, and we have see that our maximum number, suppose if this is our pi plus plane, if this is our pi minus plane, and if simply if this one is our pi plane, so our support vectors will lie on this, and non-support vectors is also here, here, and also for positive points non-support vectors lie on this region. So we are simply, if we have considered these non-support vectors, the show these portions will simply delete it, because alpha is 0 here. So these portions for non-support vectors, this portion is going to 0, and for only support vectors this we have to calculate this portion. So in runtime complexity, if you see that, so in our data set, so non-support vectors is so much, so non-support vectors point is number of non-support vector points is greater than number of support vectors point. So by using simple this query equations, we can easily increase our, so from this we can easily increase our runtime, because of this thing, because we don't care about our non-support vectors, we are only care about our support vectors. So these things are important, here we are not taking care about this portion, because of this technique, because of this, simply I'm repeating again, because of this those things, we, this system is called the support vector machine. Okay, and for this reason this dual problem is very important, and easily for a large huge data set, we can easily build a model as a low latency model, easily built, because in actual in real world our support vectors are so few, but our non-support vectors is so large, and we are simply avoiding, we are just ignoring our non-support vectors to our calculations. So for this technique is called the support vectors, and because of this, only because of these reasons, this technique is so important in early night. Okay, I think this concept is clear all of you, why this technique, why this portion, why this thing is so important. Okay.